Hello, my name is Andrew Geary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. For this episode, I speak with Joel Sarout on Maze the Leading Edge, Exploring Rock Physics. Joel highlights the 9 papers and discusses the common themes and latest advances in this growing topic. He also highlights the case studies from this special section, why new geophysicists should specialize in rock physics, and considers the next advances in rock physics. Joel Sarout is a senior research scientist at the Commonwealth Scientific and Industrial Research Organization in Australia, where he currently leads the rock properties team. He is a rock physicist by background, and his research interests lie in experimental geophysics and geomechanics, and theoretical modeling of porous and cracked rocks behavior. He holds a PhD in Earth Sciences, Rock Physics and Geomechanics from ENS Paris. To read this month's special section, visit library.seg.org. Subscribers can read the full articles in the SEG library, and everyone can read the abstracts for free. Now, for our conversation. So I want to start out with a little basic question for our audience. How would you explain rock physics to an early career geophysicist?
Well, based on my own experience so far, the way I see rock physics is essentially, let's say, the link between seismic images of the subsurface and the specific properties of the rocks at the subseismic or pixel scale, if you look at this as a seismic image. So typically, for obvious reasons, typical properties we are usually interested in include content in water, or oil, or gas, of a porous reservoir at depth. And the question really is, can we know that information without drilling a well, or at least minimize the number of wells we drill? So another question that also is often asked about a field operation is under which conditions a rock would fracture at depth if production or injection of fluids is going on. So basically, the interpretation of remotely acquired seismic data in general require some input information or guidance, either through laboratory testing, statistical modeling, empirical by nature, or theoretical modeling, more mechanistic approach. This is really where I feel rock physics sits.
This May special section for the leading edge is fairly large. It has nine papers in all, and there's been an increased interest, as mentioned in the intro, at recent SEG annual meetings. What are some of the reasons for this growing interest in rock physics?
Yeah, it's probably a bit harder to answer. I believe that rock physics has been around for years, and I've learned a lot following the steps of great rock physics influences. Rock physics is the link between remotely acquired images of the subsurface and the properties of the rocks at depth. Those are the ones we are really interested in general. So I would say it is the tool of choice to build a physics-driven and therefore increasingly predictive approach to exploration and production of subsurface resources. So I would say in a tighter economic context we are going through at the moment, process optimization, profitability increase are often required. So perhaps this is what drives this increased interest in rock physics, because it brings in a more objective way to relate what we acquire from the surface to what is really going on at depth. So in a sense, it helps better predict and constrain subsurface resources. So typically oil and gas. So this is incredibly important these days.
What are a few of the topics and case studies that these 9 papers highlight?
So that, as you say, there are 9 papers, and really what strikes me is the diversity of what is proposed by the different authors. So there are case studies, there are fundamental lab research, there are examples of modeling. So I will probably be biased by my own research interests within rock physics. So let's say I have selected a couple of papers. I would like to outline actually 2 essential and complementary aspects of rock physics. On one side is the theoretical modeling, and on the other, the laboratory validation. So this illustrates the diversity of skills required in rock physics. So, for example, the paper by Yurikov et al., as every geophysicist knows, two types of body waves exist in solids, shear and longitudinal. To characterize elastic properties in the lab, usually shear and longitudinal transducers are required. Here, what these authors have developed is a method to actually reduce the number of transducers used and their type to only shear transducers. And using this sort of sensors and some physical mechanical modeling, they basically show that they can collect shear and longitudinal data from shear transducers. The benefit is obvious because it reduces the costs and complexity of lab testing, especially for anisotropic rocks, for which 5 to 9 independent velocities are usually required to characterize properly the elastic properties of the rock. So I find this a real and effective advance in experimental rock physics. The other example I would like probably to outline is the paper by Muir and Wernick, which essentially shows a comparison of a number of existing rock physics models, so namely a patchy cement model, ellipsoidal inclusion model, and diagenesis models. And the good thing about this paper is that it shows how we can relate elastic properties of rock to their composition, mineral composition, microstructure, and the effective stress based on a worldwide log data set. So in a sense, this particular paper shows the maturity of rock physics, while it also shows that it is still a dynamic and active field of research, because matching existing models, if you allow me, optimizing the use of the best model for a specific application is still an ongoing interest. This gives a span, if you like, of what has been reported in these 9 papers.
Did anything stand out to you in editing and reviewing this special section and reading these papers of possibilities of rock physics that had not occurred to you before reading these papers, or maybe a limitation that you yourself are working on or yourself haven't seen or heard about before then?
I would say the first thing about what stood out, if you like, is really the geographical diversity of rock physics players. Just in 9 papers here, we see that they have been written and they originate from North and South America, Europe, Middle East, Australasia. Only Africa is really missing from the most populated continent. So really, although we have rock physics is a small community, it's a very diverse one. And I think this special issue reflects this particularly well. The other aspect that stood out is the span across the value chain. So the 9 papers are typically oriented towards oil and gas and fossil resources, but they show how rock physics actually applies from the most fundamental aspects of how do you get a measurement in the lab to case studies for a particular field or reservoir where it is applied and predictive information is gained, up to more general trends that can be derived from a worldwide data set, as I mentioned in the paper by Muir and Wernick. So really, these are the 2 aspects that I was pleased to see in this special section.
For geophysicists maybe new to rock physics, how would reading these articles help their own research and exploration?
The first thing that comes to mind is the fact that by publishing these papers and putting them out there for the community to see, outlines the current state of knowledge, although only in a few of the numerous subdisciplines pertaining to rock physics. So within these subdisciplines, these papers show a snapshot of ongoing research, which can give newcomers a good overview of current state rock physics and the current orientation of the research, where people are putting effort. Hopefully this can trigger interest from geophysicists to get more involved into rock physics and grow this community. Also, the detailed case studies reported in here, in particular, they show what tools are used in modern rock physics, and hopefully this would guide them in choosing rock physics and in which subdiscipline that they would like to contribute.
If there is a future special section on rock physics, what do you think you hope would be discussed in a future topic special paper?
My feeling is the future in rock physics is the digital rock physics technology. It has been going on and being developed for years, but we have seen the limitations of using images, whatever the resolution we can achieve, to actually predict the physical properties of these 3D images, if you like. So images of the internals of rocks. So CT scanner, X-ray CT scanner, neutron imaging, where we can actually see better fluids and the motion of fluids within porous rocks. I think these aspects are the future, but somehow so far a lot of effort has been put in the acquisition and improving the acquisition of these images. A lot of efforts have been put in modeling the properties of such synthetic rocks, if you like. But probably what is missing and what would be really helpful is to put more effort in comparing the output of these models based on images to actual data. And what I mean by actual data, and in view of the limitation of imaging to centimeter scale pieces of rock, how can that compare to experimental data of direct measurements of those physical properties? How fast or easy flow occurs within a porous medium, and how that compares to applying Navier-Stokes equations to fluids within porous media. So that's one aspect I think we should put a bit more emphasis on. But of course, there are many other topics, and again, I'm probably biased by my own interests, but there are things that we haven't seen published in this specific issue of the leading edge on rock physics, and probably it would be nice to see that in an upcoming special issue, more about numerical simulation of fluid flow in porous rocks in conjunction with experimental measurements. And non-seismic applications. So here we always implicitly think rock physics is elastic properties, but in fact, it's way more general than that. Measurement of thermal properties for the recovery, to help recovery of geothermal energy, electromagnetic properties of rocks. All these are ongoing aspects of the global effort in research, but probably rock physics should be dealing a bit more with these aspects.
What do you hope readers of this special section will take away?
Yeah, it really depends on the papers. Again, the case studies are probably the ones that would be more easily digested and probably the best to show really the breadth of skills that are actually required to achieve this kind of large-scale analysis. That's really something where everyone who has dealt with a bit of physics, a bit of mechanics, so I'm thinking geophysicists, rock mechanicists, geomechanicists, could actually find something in there in which they can contribute. Because basically these case studies they encompass a number of skills, and without this multidisciplinary approach, these workflows won't work. So rock physics in that sense is quite a wide topic. So everyone actually interested in quantitative science can find something to apply his or her skills to, or push beyond the existing.
Well, it sounds like it's going to apply to a lot of scientists out there.
Yes, I believe so.
What should I have asked you that I did not?
Yeah, probably. One point that I feel could be a limitation these days. This set of papers basically illustrates well the opportunities for applying physical and mechanical principles to various problems in geoscience. But one key limitation, I believe, is, with the global increase in the need for numerical simulations, advanced data analytics, artificial intelligence, I'm under the impression that some subdisciplines within rock physics, namely digital rock physics, are growing, yet at the expense of more laboratorial research. Again, this reflects a bit of a bias, I admit that, but it seems to me that analyzing large sets of existing data is attracting more attention and effort than deriving new or more accurate or more reliable data from the laboratory. This is my impression these days, and probably this makes sense in the sense that lab research is known to be expensive and requires long-term commitments to purchase equipment and develop the technology around these sort of measurements. So this seems to somehow deter possible research sponsors, and which seem to be more attracted by the faster output of so-called numerical experiments. I hear that a lot, and when I review papers, I see that often, that now numerical simulations and laboratory experiments are somehow mixed into a terminology. An exotic one for me is numerical experiment. So basically, rather than running lab experiments with all the issues related to it, the uncertainties, the costs, we prefer, probably because it is probably more cost effective, run numerical experiments in which we input a known laws of physics and mechanics and try to extract information or predict. And although this is a useful exercise, no doubt about it, I doubt that you can find something new by only putting things that you know of. So numerical experiments, I would like to never hear this word again, so that we don't end up doing laboratory simulations and numerical experiments and mix up future readers. So basically, yes, numerical simulations are good, but you only input known information in there, while laboratory experiments are fundamental in the sense that the unknown is what you're dealing with. So, of course, we try to minimize this amount of unknown by controlling the parameters we vary, etc., etc. That's the typical laboratorial approach. But I think we need more of this. And it seems to me that for cost effectiveness, this aspect is going rather down relative to numerical simulations. So that would be one point I would like to highlight because I have the opportunity today.
Well, take advantage of it. That's a good final call to your fellow scientists to put in their mind, and hopefully will listen to you. Thank you for your time and for speaking with me today. It's been a pleasure. Thank you for making this work out and setting up this time.
Thank you. Thank you very much, Andrew, for also taking the time in view of the 12 hours difference we have. And thank you for giving me this opportunity to speak.
Please share this episode with a friend, colleague, or manager that would enjoy hearing this episode. Your recommendation is the single best action you can take on behalf of SEG's podcast. Go to our website at seg.org/podcast to find all our episodes and learn how you can subscribe for free directly on your phone. Original music by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary. The SEG podcast team is Jennifer Crockett, Ashley Rodriguez, Allie McGinnis, and Mick Sweeney. Thank you for listening. This is Seismic Sound Off, signaling off.